Hello everyone. My name is Sasan Dolati. I'm a structural engineer from Stantec, and the work is for my PhD in UT San Antonio. My advisor, Dr. Adolfo Matamoros and Wasim Qanu. In this presentation, I'm going to speak about the effects of loading, history and the behavior of reinforced concrete column, more specifically on the drift capacity and in a scale of deformation. So the outline is I will talk about the problem, the recommendation for nonlinear finite element analysis, and then the effect of loading for reinforced concrete column under seismic loading protocol. Okay, the first thing is that many existing concrete buildings, they do not satisfy the current seismic code. And by research, it is found that the collapse of concrete building mostly is due to light confinement of concrete column. These buildings are in California right now, about 23,000. And if earthquake with high intensity happen, it may have $28 billion damage, and 8,000 people are alive are in the matter. And based on the research, it is found that the loading history, the type of loading that the earthquake can happen on this column can affect the behavior of this column significantly. So we try to focus on loading history, what would be the damage if the earthquake would change their loading. We select 21 reinforced concrete column with different types of failure, 8 of them flexure shear, 4 of them shear failure, 4 of them flexure failure, very ductile format, and 9 of them with the shear failure control. Those columns that we selected, we try to cover several parameters like the type of the failure, the dimension from the 0.5 meter to 3 meter, the shear span to depth ratio that shows the stress, the different transverse reinforcement ratio, and different longitudinal reinforcement ratio. We use Athena as a software for finite element analysis. So this is the slide that shows our calibration to experimental results. You can see the orange plot for the experimental, and the blue is the finite element analysis that we did to calibrate the model. The first one is deformation with the shear base, and the other plots are showing the axial displacement. And in the top, you can see that the experimental failure versus our prediction with Athena that shows that the crack development like the experimental. Also, we see that the transverse reinforcement shows that they are having a red color here. That shows that they are in a high stress, and we expect these columns to have the yielding part in the transverse reinforcement because they are failing by shear, and shows the concrete crushing as well. The other column is tested under 3-cycle axial load, low axial load, and 3-cycle lateral load. Shows we can see the experimental failure and the model that our model that shows the crack as well. The plot again, the orange with the blue one, and shows the force deformation and the axial displacement. Again, we can see that the transverse reinforcement are red, shows that they are yielding, and the concrete shows that the hinge region has the failure as well, crushing is happening. We develop a guideline for this concrete model, and based on the guideline, we see that the amount of error that we had for 21 reinforced concrete column, we are in a trustable range. We have several zero error for point D, and some zero and some low amount of error for point C. So point C is the deformation that the column failed laterally. ASC 41 call it lateral degradation. This is the point that 80% of the maximum strength of the column happen. And point D is the point that the column can no longer handle axial load, and in the other word, the building collapse. So we are focusing on these 2 points, point C and point D. And we see that the model that we developed based on the experimental have a trustable error for point C and point D. Based on our model, we attend the Berkeley competition, the PER, Pacific Earthquake Engineering Research Institute, and they had the reinforced concrete column and they applied the lateral load. They gave us the sketch for how the reinforcement, and they didn't release the result for about 4 months. We attend the competition based on our guideline using the software Athena, and we model the transverse reinforcement, we model the boundary condition, everything like the experimental. And one of the parameters that they asked was the shear capacity. We were one of the winners between the 40 countries, and it shows that our result matched the experimental in a very good range. So the standard shows very conservative, and our model was very close to actual test. One of the purpose of the test at UC Berkeley was that the code is conservatively predicting the strength of the concrete column, and it's causing a huge amount of expense for retrofitting those buildings, which so they are not retrofitting those right now. And the purpose was to show that maybe some of the buildings, they do not need to be retrofitted for the earthquake, and they're actually right now doing fine. After that, we applied different type of loading. So we applied 1 cycle, 3 cycle, 6 cycle as a lateral load, but in a different axial load level. So until now, we have a trustable model that we know that, that we have a reinforced concrete in our lab. And we know that column that can handle everything that we want. And we started to applying different type of earthquake, different type of lateral load to see what would be the damage. So we did that by change of lateral load and by change of axial load. We have almost 0 axial load. We assume that what would be the behavior when column there isn't any axial load. This is not typical. Usually building is under axial load of 0.2. So we have about 0.15, 0.2 as axial load, and we tested for high axial load as well. So we made about 116 reinforced concrete column to see what would be the damage. And this is the sample right now. So these are the sample for 2 column. You can see that the experimental result is the red one, the triangle. We have it for 3 cycle and the axial load of 0.25. But we tested under 0 cycle, 1 cycle, 3 cycle, 6 cycle, and different axial load levels, 0.5, 0.25, and 0.1. On the other one, on the different column, again, the experimental test was on 2 cycles, 0.5. We tested on the different axial load level, 0.5, 0.2, and 0.05, and on the different lateral load, 0, 1 cycle, 3 cycle, and 6 cycle. So we made a matrix to cover from low axial load to high axial load, from 0 lateral load, just monotonic, to a lot of number of cycle, to see what would be the damage. This is the sample of the plot that we have. So this is a column, we call it 3CLH18. This is a column that's controlled by shear. These are very brittle ones. We don't want them to have them in our building. And we tested this column under low axial load, 0.08, almost no axial load, under middle axial load, which is typical building right now, and under high axial load. And we tested like monotonic, 1, 3 cycle. Let's walk through the plot. So on the plot, you see the deformation, the drift ratio, and the lateral load. And red one in all the plots shows the monotonic. There isn't any cycle. We just push the column, push the building, like in Seattle, the earthquake happened. If the earthquake happened based on the plate, we expect that it just push the column. One time we push them 1 cycle, the green one time we push them 3 cycle for each amplitude, and one time we push them 6 cycle, the black one. And we got the plot for different lateral or different axial level. And we extract the data that we wanted for analysis. So based on the plot, we got the 2 plots very interesting here. So the y-axis defined as a delta capping, and the x-axis is defined as a NCDR. So let's walk through that. Delta capping is the deformation capacity for cyclic divided to deformation capacity to monotonic. So in the other word, the point that the cyclic fail compared to the point to the monotonic fail, and NCDR is normalized cumulative drift ratio. So what does it mean? It means that the sum of the drift ratio, the sum of the displacement that the columns goes for cyclic compared to monotonic. And we extract the plot for all 116 column. You see that because it is normalized to monotonic, we always start at same point for all the column, and then we see the drop. So for green shows the 1 cycle, for the black shows 3, and for the red shows monotonic. And based on this drop, we found an equation, and which we will talk about. So we had this plot. Each plot shows the column under different lateral load. For example, this red one shows that the column is under monotonic, and the blue one shows under 3 cycle, the green one shows on 1 cycle, and the black one shows under 6 cycle. So we proposed the drift capacity equation. The drift capacity that we proposed, we call it beta, and one of them for axial, one of them for lateral degradation, and they are dependent on the longitudinal reinforcement ratio and the axial load ratio for both of them. And based on that, so we can find the reduction in the drift for different types of failure. We validate our equation. Let's walk through the table. This is the interesting one. So we have the experimental results for a column under cyclic loading and monotonic loading. So the test has been done in Berkeley by Dr. Sasan. And they have a same column. They just push it monotonically one time. They got 2.76 for lateral failure, and they got 4.96 for axial failure. Then the same column, they rebuild the same column, and they applied 3 cycle instead of just monotonic. And they got 3.1 for lateral failure and 6.45 for axial failure. So these are the real actual tests in Berkeley. We developed an equation and we used that. So we got 2.76 for monotonic. It's a bit conservative to the axial one. And we got 5.6 with our equation for monotonic axial failure is a bit conservative again. We use that when compared with the ACI 369. The whole purpose of the research is to adjust ACI 369 nonlinear modeling parameter. And we compare them with the result as well. You see that for the cyclic 2.5, we got a bit again conservative to experimental, and 5.6, we got a bit conservative to experimental. The ACI is doing the same. It's somehow conservative to experimental. In one of them, it's not conservative, and it's a bit higher than the experimental result, which we are working on that right now. So, by conclusion, we have 21 reinforced concrete column. We use finite element analysis software Athena, and we develop a guideline. We publish that guideline in ACI, and that one covers several types of failure. And right now, anyone can model reinforced concrete column. And we have 18 reinforced concrete column. We applied 3 levels of axial load, and we made 116 simulation. We developed the drift capacity equation. We validate those, and we found that when we increase the axial load, the effect of cycle is high for high ductility, and when we increase the axial load for lateral degradation, the effect of cycle reduce. Any question?